So in this first lesson of complex numbers, we're going to look into the history and motivation behind this subject. So we all know the quadratic formula, and its purpose is to solve for the roots for any quadratic. But we know that we can run into problems with this quadratic formula, and that is when we apply it to certain quadratics, we run into the discriminant being negative, and so we can't find the roots of the given quadratic. But when this situation arises, what's really happening is that the quadratic looks something like this, and it has no roots at all. So the algebra here is messed up and doesn't work because you're trying to attempt to find something that doesn't really exist. So the thing about this situation here is that there's no need to push this matter any further. There's no loose ends. There's nothing wrong with this whole situation here. Everything's consistent and makes sense. The algebra here is not working out because you're attempting to find something that doesn't really exist in the first place. So with this quadratic thing, the negative square root occurs when there are no roots. So this whole quadratic story is really done. It is just finished here. There's nothing else to discuss about quadratics. But after solving this quadratic issue, the natural next extension that we want to make is ask the exact same question, but now for the cubics. So that is, we have a powerful formula that allows us to solve for roots of any given quadratic. So now we're after something called the cubic formula. Is there an analogous formula for the cubics that does the exact same job as this guy, but for quadratics? So in other words, is there a formula that we can find and discover such that given any sort of cubic, I can run the formula and the formula can give me all the roots to this polynomial here? And it turns out that this question is actually really hard. Just increasing this degree by 1 increases the difficulty of finding this formula by heaps and heaps. Okay, but there's one more really big distinction between these problems, and that is when you draw quadratics, it's possible for them to not have any roots at all. But because a cubic bend looks something like this or this, no matter how you decide to draw a cubic bend, there's actually no way for you to avoid the x-axis. So this means that cubics will be guaranteed to have at least one root, no matter what. So let's keep this keep this fact in mind. We'll come back to this very soon. Okay, so the goal is to try to find the cubic formula for this thing. But it turns out trying to do that directly with this expression for the cubic is actually too hard. So what we're going to do is an algebra trick. And the trick we're going to do is a substitution. So what we're going to do is let x be z minus b on 3a, where b and a are just these coefficients from the given cubic. So we're going to let x be written in terms of this new polynomial here. So if you let this substitution happen, that is, take this thing and place it everywhere you see x, and if you grind through that really terrible long algebra, you're going to get something like this. So this thing looks kind of scary, but these b's, a's, c's are just coefficients that's been chosen from the original cubic. So this mess here is secretly just some constant number in the end, despite being a mess. So, and obviously the same thing can be said here. So I'm going to label this constant number as just some number p, and this is just some number, and it's going to be q. So therefore, doing this substitution actually allows us to simplify the original given cubic down to a much simpler form. And this is called the depressed cubic because the quadratic term has been completely disappeared after this substitution here. And again, it's important to remind us that p and q are just in terms of the original coefficients, these b's, a's, and c's. So they're just fixed constants. And doing this is useful and actually solves the original question because if we can solve this question, namely we can find a z to make this equation true, we can find an actual value of z that does that. Well, if you have that value of z, that means you have solved the original question of finding x as well. Because if you know the value for z, you just put it here, do the subtraction, and you obtain the relevant number for x itself. Okay, so instead of asking what is the cubic formula for this directly, which is too hard of a problem, we reduce the problem from this to this, and now we're going to ask what's the cubic formula for this instead, rather than this thing directly. So even though we simplified the question, unfortunately, while we have solved this question, we found the formula, but unfortunate thing about the formula is that the formula actually looks like this. So it's much worse looking than the quadratic formula itself. Okay, so we found the cubic formula. Let's try and use it. So it has the ability to solve any cubics in this form. So let's just try one out. Let's try this one. So here P will be 3, Q will be 18. And if you pump these numbers into this formula, you get something like this. And if you try this number out on a calculator, it will work out to be exactly 3. So 3 would be a root of this particular cubic here. And the graph of that cubic will look something like this. So everything looks good so far, the formula is working. But notice how P and Q, right? P and Q is just whatever numbers we can choose to express the cubic in. It's just whatever coefficients we can pick. So P and Q are completely up to us, and P and Q are part of this giant cubic formula that we need to use. So what that means is that if these two numbers are just up to us to pick, then it is possible to have a choice such that this expression hiding within this square root can be negative. So let's see an example of that. Like if I just pick P to be 15, Q to be 4, and we run the formula, you can see that this is going to be negative because if you put 4 here, 2 divided by 2 is 2. 2 squared is definitely a number that's less than 5 cubed. So in fact, it will work out to be minus 121. So you can see that we run into a huge issue here because again we have a negative number hiding inside a square root. But this is actually even worse of an issue than what it was back with quadratic equations. Because what happened in quadratic cases? Well, if it was a negative square root, that was the case for which the roots just didn't exist. So we just completely ignored that thing. But remember the issue with cubics, right? Cubics has to have at least one root, like no matter what. So we can't just do what we did before and just completely ignore this thing and just move on. Because this thing has to stand for one of the roots of the cubic somehow. And in fact, like you can just test that 4 will work. Like 4 is definitely a root of this thing because if you substitute 4 in here, you get precisely 0. And in fact, if you ask computer to graph this cubic, it will look like this, and one of the roots is clearly 4. So for some crazy reason, this expression that we can't really handle right now, like it's magically just equal to 4, like somehow. So this is the thing that we want to focus our attention to right now. Okay, so this really weird expression on the left hand side here, it's equal to 4 somehow. And we're just going to work and play around with this expression on the left. The first thing we're going to do is, notice how we just got kind of a random number inside the square root. But luckily 121 is 11 squared. So I'm going to take this 11 squared out of the surd. So we just become 11. Now we're going to focus our attention to this little bit here. And this thing is going to play a key role. So I'm going to label this number here, this new weird number, with the letter I. So if I is the square root of -1, then I has this property such that when you square it, we're going to get -1. Okay, so this weird expression here, under this new notation will look like this. So we're just replacing this bit with I, which is writing the same thing. Okay, but this thing is really crazy because right now, like we just gave it a letter, but we don't really understand what this number actually means. So we're going to this weird number that we're not familiar with. We're timesing it by 11 somehow. And not only that, we're going to go to this weird number and add the usual number 2 to it. So right now, we don't know how to handle this number at all. And even worse, this expression is actually asking us to take the cube root of a number that we can't even handle in the first place. So this question is actually really difficult. So for a long time, a lot of people didn't know how to handle this thing, but people had the intuition of just guessing what this should come out as. And people guess that this expression somehow should just be equal to 2 plus ni, where n is just some number. They have this intuition, this made this random guess because, well, remember, this thing has to somehow equal to 4. So if you made this guess, and you can see that this guess will work, like if you add these two things, these two bits will just cancel and you do in fact get the 4 back. So this is a random guess. We're just guessing that this bit here, hopefully, is equal to like 2 plus ni for some value of n. So let's try and find what this correct value of n should be. Okay, so we're deliberately setting this to be equal to that, and we're trying to discover what the value of n should be. Okay, so working with this, we're going to take 3 powers of both sides. We get this thing. If we expand this bracket out, we're going to get this thing. Okay, so here we got an I squared appearing, so we've got to be careful here. So I squared, remember, is going to be -1. So this term over this whole entire term will end up being -6. Here we got an I cubed, but I cubed is I squared times I, but I squared is -1. So we're doing -1 times 1 more power of I, giving us -I overall. So this will become this term here. Okay, so just rearranging this thing on the right a little bit, and also factorizing the common i's out from these two terms, we're going to obtain this thing. Okay, now you can see that the coefficient of I on the left is 11, and this guy is playing the role of the coefficient for I here, and if these two expressions were to equal to each other, these two coefficients has to equal. And if these two bits were to equal, then the remaining red parts themselves have to be equal as well. So you can see that we set up a pair of simultaneous equations here. Okay, going to the first equation, solving it, we get the answer of ±1. But at the same time, this stuff has to satisfy this equation, and so the only solution would be +1 itself. Okay, so from this work here, we worked out n should be 1 to make this happen. So n is 1. So this is just somehow 2 plus I, and that's 2 minus I. And you can see that this is working. So this is rigged to 2 plus 2 to be 4. Okay, so this cubic formula for solving roots problem is like solved, kinda. But really, in the process of solving this thing, we actually created more questions. And one of the most important questions is like, how to actually interpret this new mysterious number here. Like, what is it? And with real numbers that we're familiar with, like, there's a way for us to like visualize it geometrically. They're just points on these number line, right? So this is a new type of number, and a really important question is like how to view this geometrically. So we can view real numbers geometrically. So what will I look like? How do we visualize it? And furthermore, when we were like tackling this question here, right? Like the question is suggesting that we need to take these weird new numbers and they somehow interact with regular numbers that we already have. So that interaction can be expressed like this. So new weird number by interacting with old familiar numbers. And the question is like, how do we deal with these numbers? How to interpret them and how to view them geometrically? So we're going to look into these questions in the next video.